In May 2017, security researchers forced Intel to publish an emergency warning about a flaw buried far below Windows, Linux, and every antivirus program. The vulnerable code lived inside Intel's management firmware, a system most PC owners had never installed, never configured, and could not simply uninstall. It ran before the operating system, could remain active while the main CPU slept, and on supported business machines could participate in remote management. For privacy-focused users, that discovery crystallized a disturbing problem. Owning the laptop did not mean owning every computer inside the laptop. Hidden beside the processor was another processor, with its own firmware, its own memory access, its own privileges, and almost no user-visible interface. Years later, a small European laptop company began selling machines built around a very different idea. Let the owner inspect and rebuild the firmware. Nova Custom paired its laptops with Desharo, an open-source firmware distribution built around Coreboot, and, on some models, the head security environment. Inside, Desharo's setup menu sat an option rarely exposed by ordinary PC vendors: Intel Management Engine mode, including a HAPI-based disabled state. That sounds like the final answer to a problem privacy engineers have argued about for more than a decade. But the truth is more complicated. Desharo does not erase every proprietary component from modern Intel hardware, and the management engine is not proven to be a surveillance backdoor. What it does offer is something conventional consumer firmware almost never gives you: visibility, control, reproducibility, and a way to reduce ME activity. The real breakthrough is not a motherboard with no opaque code. It is a machine designed so the owner can finally see where the opaque code remains. And that distinction matters because the Intel management engine was never an ordinary application. It lives in the platform itself. Intel describes ME and its newer CSME variants as embedded controllers that run firmware separately from the host operating system. It can initialize platform functions before your OS starts and operate in power states, where the main processor is asleep or otherwise inactive. On systems equipped for Intel active management technology, that architecture can also support out-of-band administration independent of the normal desktop session. To an enterprise administrator, those features can be valuable. To a user seeking a minimal trust base, they create the opposite feeling. If a privileged subsystem is always present, closed, difficult to audit, and required for boot, then who ultimately controls the lowest layer of the machine? That question is where Nova Custom and Dasharo become interesting, because their answer is not to pretend the subsystem never existed. Their answer is to open as much of the surrounding firmware as possible, expose the controls vendors usually hide, and contain what cannot yet be removed. The story begins with Coreboot. Conventional PC firmware is usually distributed as a large vendor image containing initialization code, drivers, setup interfaces, compatibility modules, and numerous binary components. Users normally receive the final image, not a complete recipe for rebuilding it. Coreboot attacks that model by replacing much of the traditional firmware stack with an open-source project focused on performing the minimum hardware initialization required to hand control to the next stage. Coreboot is not automatically blob-free. Modern processors still depend on proprietary microcode, silicon initialization components, management firmware, and device firmware whose source code may not be public. But Coreboot changes the architecture around those dependencies. Instead of treating the entire firmware image as an indivisible black box, it lets engineers identify which portions are open, which portions are binary, why those binaries exist, and where they execute. Desharo builds on that foundation. Developed by 3M Deb, it packages Coreboot with security features, testing, documentation, update mechanisms, and payloads intended for real hardware rather than laboratory demonstrations. Nova Custom ships supported laptops with Desharo variants, including Coreboot with UEFI, and on selected models, Coreboot with heads. By 2026, Desharo documentation listed multiple Nova Custom generations, including Alder Lake NV41 systems and newer Meteor Lake V54 and V56 machines. That is why calling this an open-source motherboard is both useful and misleading. The physical board itself is not a completely open hardware design with every schematic, controller, silicon block, and firmware source liberated. What is open is a much larger part of the boot firmware stack than on a typical laptop, along with build instructions that allow technically capable owners to compile Desharo themselves. The ownership gain comes from firmware transparency, not from turning Intel silicon into open hardware. And the hardest proprietary component in that picture is ME. Intel's own documentation describes the management engine as a microcontroller integrated into certain chipsets, running a lightweight microkernel and loading code from system flash. Modern CSME implementations include their own processor, memory, cryptographic engine, and I/O isolated from the host CPU. In other words, the machine contains a security computer supervising parts of the machine you thought was the security boundary. That architecture exists for legitimate engineering reasons: platform initialization, secure boot functions, Hardware authentication, licensing services, power management, and enterprise manageability all benefit from a controller that does not depend on the main operating system. Intel AMT, when present and provisioned, can give administrators the ability to diagnose and manage systems even when the normal OS is unavailable. In a corporate fleet, that can save enormous time. But capability changes the threat model. The same isolation that makes a management controller resilient to Windows crashes also makes it difficult for the Windows user to observe. The same network-independent management path that helps an administrator recover a machine can become serious if a vulnerability appears in the management stack. And unlike ordinary software, this firmware is not something most users can replace with an alternative package from another developer. The fear stopped being theoretical in 2017. Intel disclosed Intel SA0075, a critical vulnerability affecting management features on certain systems. Later that year, Intel published another major advisory covering vulnerabilities in ME, Trusted Execution Engine, and Server Platform Services firmware. The details and affected configurations differed, but the lesson was unmistakable. Code below the operating system can contain exploitable flaws too, and fixing it depends heavily on firmware updates supplied through the hardware manufacturer. The important correction is that documented vulnerabilities do not prove Intel deliberately built a spying backdoor. There is no credible evidence that every ME-equipped consumer laptop secretly records users or continuously transmits private data to Intel. Conflating architectural privilege with proven surveillance weakens the real security argument. You do not need a conspiracy theory to care about an unauditable component with high privilege. Attack surface alone is enough. The deeper concern is trust concentration. ME firmware is signed, tightly integrated with Intel platforms, and essential enough on modern generations that simply deleting it can prevent normal boot. Descharo's own technical documentation is explicit. Starting around the Nehalem era, completely removing functional ME firmware is generally not an option on supported modern Intel systems. Some initialization code must remain because the platform expects it. This is where a famous open source tool, ME Cleaner, enters the story. On compatible older ME generations, ME Cleaner can remove non-essential firmware modules while preserving the portions needed for platform initialization. Coreboot documentation describes the process as cleaning or reducing the ME region, not replacing the subsystem with an open implementation. The result can dramatically shrink what remains, but it is platform dependent and can cause hardware problems if used without careful testing. Descharo therefore uses another mechanism that is often more practical on newer machines, the High Assurance Platform, or CHA-P disable bit. The setting lives in the Intel flash descriptor. When applied on supported ME generations, it instructs the management engine to halt after the early initialization it must perform. Descharo exposes this as an Intel ME mode option, and its documentation distinguishes HAP disabling from softer methods that send disable commands later through the host interface. That detail changes the entire interpretation of the Nova Custom machine. The goal is not to rip ME physically out of the chipset. The goal is to let it perform the minimum platform bring-up that the silicon requires, and then stop it as early as the platform permits. Descharo also hides the MEI, or HCI interface, from the operating system when ME is disabled, further reducing interaction with the host environment. Why does Intel provide a mechanism capable of doing this? The historical answer is one of the stranger details in modern PC security. The HAP mechanism became widely known after outside researchers examined Intel firmware and identified a disable path associated with high assurance requirements. Descharo's own documentation describes CHA-P as a kill switch-like control that leaves ME stopped after initialization. That means the platform vendor itself designed a way for certain deployments to minimize the subsystem's runtime presence. For privacy-oriented buyers, Nova Custom turns that obscure capability into a normal firmware setting. That is, the part traditional laptops almost never expose. Instead of accepting whatever ME configuration the OEM selected at the factory, the owner can choose between enabled, soft disabled, or HAP disabled modes where supported. Some Descharo configurations and heads-based offerings use HAP disabling as part of their security posture by default. But control has consequences. Descharo documentation warns that some sleep behavior depends on ME. On newer Intel systems, modern standby, known as SOX, may not function properly when ME is disabled. Users may need classic S3 suspend RAM where the hardware and operating system support it. That trade-off is important because sovereignty is not free. Removing a privileged subsystem's runtime functions can also remove legitimate power management services tied to that subsystem. This is exactly what makes the project credible. A fake, deblobbed laptop would advertise total freedom and hide the breakage. Desharo documents the limitations. It explains which components remain, which features change, which update paths are supported, and which platforms still have known issues. In its 2026 release notes for Nova Custom hardware, the project continued publishing precise firmware versions, test results, Intel ME versions where applicable, and unresolved problems. The transparency becomes even more significant when you compare the update process. On a conventional laptop, firmware updates often arrive as opaque executables or signed capsules from the manufacturer. You trust that the vendor built the image correctly because you have almost no practical way to reproduce it. Desharo publishes source repositories and build procedures for supported Nova Custom laptops, including separate instructions for the embedded controller firmware and the Coreboot-based BIOS image. A technically capable owner can clone the source, check out the release revision, build the firmware, and compare what is produced against the expected release artifacts. That does not automatically guarantee a perfect supply chain. Reproducible builds are difficult, and Desharo's own release notes have acknowledged places where exact reproducibility was still incomplete. But the security model is radically different because verification is an engineering goal instead of an impossible request. The embedded controller is another overlooked part of this story. Laptop users often focus on BIOS and ME, yet the EC controls things such as the keyboard, battery charging, thermal behavior, and power sequencing. A system could replace its BIOS with open firmware and still leave a highly privileged embedded controller running closed vendor code. Nova Custom's Desharo-supported laptops have increasingly incorporated open-source EC firmware, and the project documents building that component separately. That does not make every chip transparent. Storage drives run their own firmware. Wi-Fi adapters run firmware. USB controllers, GPUs, Thunderbolt controllers, and modern CPUs contain microcode or internal processors. Even a laptop with Coreboot can contain several proprietary islands. The meaningful question is therefore not whether the machine is 100% open. On contemporary x86 hardware, that standard is extraordinarily difficult to meet. The meaningful question is how small, visible, and controllable the remaining trust base can become. Heads pushes the answer further. Originally developed as a security-focused firmware environment, Heads combines Coreboot with a minimal Linux environment and measured boot concepts designed to help the owner verify that the machine has not silently changed. On supported Nova Custom models, Desharo offers Heads-based firmware as an